Okay, 15.6 is the last section of chapter 15, and it's going to talk about equilibrium in the context of Le Chatelier's principle. I don't speak French, but Le Chatelier's principle is how I would pronounce it. And it seemed fancy enough to deserve some nice cursive writing up there. So Le Chatelier's principle is an easy way to predict how a system is going to respond in order to reach equilibrium. In particular, if you have a system which has already reached equilibrium, and then you introduce some change to perturb it away from equilibrium, then it's going to respond in order to restore that equilibrium. The sorts of changes we could do is change the concentration of one of the reactants or products. We could add or take away some of that substance. We could change the volume of the system. If it's a gas, we could compress it in a piston. If it's a aqueous reaction, we could, say, dilute it by dumping in a bunch of solvent or boil away some of the solvent to concentrate it. And then another change is that we could change the temperature, heat it up or cool it down. And all of these things are going to disturb the system to push it away from equilibrium. And then the chemical reaction will shift either toward reactants or products in order to restore that equilibrium. And so we could, of course, look at the new conditions after we've made the change and calculate the reaction quotient and compare it to the equilibrium constant K. And remember, if Q is less than K, then the reaction is going to need to shift to the right. And if Q is greater than K, then the reaction will have to shift to the left. But Le Chatelier's principle allows us to make these determinations without actually calculating Q, without doing any math whatsoever, which makes it really quick and convenient. Okay. And so let's first talk about adding or removing product. Let's consider this reaction right here. 2H2S gas is in equilibrium with 2H2 gas plus S2 gas. Okay, there's our equilibrium. If we assume that this reaction has come to equilibrium and then we add or remove reactants or products, how is it going to respond? There's a couple of different ways to think about this, and one of the analogies that we can use is to say that this equilibrium reaction is like a U-pipe with open ends. And if you put some water into either end of that U-pipe, the water will flow through the middle until the water levels have equalized themselves. That's just how water works under gravity. Right? And so having the water levels equal to each other is, in this analogy, equivalent to the system being at equilibrium. And then we can add or remove things from the left side to represent reactants, add or remove things from the right side to represent products. So let's talk about adding H2S. If I add H2S into the reaction system, that would be like dumping a bunch of water in this left side of the U-pipe. And hopefully you have a bit of an intuition about which way is the water going to flow. If I dump a bunch of water in the left side, it's going to flow toward the right. This water level will have raised, and then this water level is going to have to rise to match it by water flowing to the right. And that's basically what happens with the chemical system as well. If we add H2S, then in order to respond to that change, the system is going to act in a way that sort of undoes our addition. It's going to consume some of that extra H2S and generate more hydrogen and more sulfur. Okay, what if, let me erase my arrows here. What if I remove H2S. Okay, so that's a funny arrow. Okay, what if we remove H2S? That would be like sucking a bunch of water out of this side of the U-pipe, and of course the water is going to respond by flowing back there to replace it. So removing reactant will shift the reaction to the left. If we remove some H2S, then in order to reestablish equilibrium, some hydrogen and sulfur are going to react together to regenerate a portion of what was removed. And we can say the same things about, I'll go ahead and erase my U-pipe analogy. I think it makes enough sense without having to redraw it every time. So we can say the same thing about the products. If I add hydrogen, which way will this reaction shift? Well, it will have to get rid of that extra hydrogen, or at least a portion of it, by going in the reverse direction. So add hydrogen is going to go to the left. Even if I didn't add S2, right? I only need to add one thing to upset the equilibrium. If I remove S2, then that's going to go to the right. Okay, there's one important part of this, part of Le Chatelier's principle, and that's that it only applies to species which appear in the equilibrium expression. Solids and liquids do not count. If I have a reaction that has some solid in it, for example, adding more solid or taking some amount of the solid away is not going to upset the equilibrium at all. And the same thing for liquids, as long as the total system volume remains the same, and we'll get into volume changes later. Actually, let's get into volume changes right now. Okay, so let's consider N2 gas plus 3 H2 gas in equilibrium with 2 NH3. And let's think about what will happen in this gas phase reaction if I change the volume. Let's suppose I have the reaction in a piston with a movable head, and it reaches equilibrium under one volume condition, and then I pull the piston upward, and V2 is greater than V1. In fact, let's give real numbers. That might make it even easier. Okay, let's say I double the volume. V2 is equal to, 2 times V1. Well, have I added or removed any of our reactants? No. And they were under equilibrium before, and so you might wonder, are they going to be affected at all? Does that change the equilibrium? Well, let's kind of analyze what the effect of that would be. So we know that under our original equilibrium conditions, then we had the concentration of NH3 squared and the concentration of N2 times the concentration of H2 cubed. Okay, that is what our original equilibrium condition was. Now, when I doubled the volume, when I pulled up on that piston head and doubled the volume, how did each of these concentrations get affected? Well, they all got cut in half. And so what we really have is 1/2 times the concentration of NH3 squared. And by the way, this may or may not be at equilibrium, so let's, for now, let's just call this Q. Right, we doubled the volume, and let's see how it affected the equilibrium. Well, we're going to have 1/2 of the nitrogen concentration and we're going to have 1/2, I can't really fit it in there, sorry, 1/2 of the hydrogen concentration cubed. And this is, of course, going to equal our initial nitrogen concentration over our initial our initial ammonia concentration over our initial nitrogen concentration over our initial hydrogen concentration. That's squared and that's cubed. And I can take all of these 1/2s and I can cancel some of them out. I have 1/2 times 1/2 cubed, that's 1/2 to the 4th power in the denominator. I have 1/2 squared in the numerator, and so these two will cancel out with 2 of those. I'm left with 1/2 squared in the denominator, which is also the same as 2 squared in the numerator. And so if our initial amounts were the equilibrium constant, then it looks like Q, after I've doubled my volume, is equal to 4 times the equilibrium constant. That means that Q is it's no longer at equilibrium, and we are going to have to shift toward the left in order to reach equilibrium. And that may be a surprising result because we haven't added or removed anything, but the fact is that by changing all of the concentrations equally, by cutting them all in half, we've pushed the system away from equilibrium because some of those concentrations are squared or cubed or raised to the 1st power, and so they don't all cancel out. And so that's kind of a mathematical derivation, and Le Chatelier's principle is all about developing quick, easy tools so that you don't have to actually do the math. So let's generalize this. Okay, this is a gas as well. What really mattered was the number of moles of products and the number of moles of reactants. The reason why the 1/2s didn't cancel out is because we had only 2 product moles and we had 4 reactant moles. And so, if I increase the volume, then what I should really say is not that it's going to go left or right. In this particular case, it went left. But what it's really going to go is go toward the side with more moles. In this case, we had 4 moles over here and 2 moles over there. And we could play the same thing for a decrease in the volume. So we decrease the volume, and that's going to have the opposite effect. It will go toward the side with fewer moles. Go to the side with fewer moles. And if you want kind of an intuitive way to think about this, I just imagine decreasing the volume is pushing everything closer together. In the case of a gas, it would actually correspond to an increase in pressure. And so you're pushing everything closer together, and if they can undergo a reaction to change 4 into 2, well, that's going to relieve some of the strain of pushing so many things into a smaller volume. Right? So it's like you squeeze them from 4 into 2 by undergoing this reaction. And then if we increase the volume, then that's making more and more and more space for all of the reactant and product molecules. And because there is space to because there is space to spare, then they will undergo a reaction, say, from 2 to 4 in order to better fill that space. And that's just kind of maybe a bit anthropomorphizing the molecules, but it is a kind of more tactile and intuitive way to think about this. Now, we increase volumes by adding solvent. So if this is an aqueous reaction, just dump in some water. Or we can increase the volume for gases by decreasing the pressure. When I pulled up on that piston head, like what that meant was that there was a lower pressure inside the piston because of the increased volume. You can think back to PV equals nRT to convince yourself of that. Then we'll decrease volume of aqueous reactions by boiling away some of the solvent. Or for gas systems, that's actually going to be increasing the pressure. You need to push down on that piston head with external pressure and increase the pressure inside the system. Really, it's the volume that matters, but for gases, sometimes it's easier to think in terms of pressures. So, I forgot to set up the slideshow, so I'm going to pause this. And we see here figure 15.6 just kind of illustrates this principle. On the left, we've got the largest volume, and we have the largest proportion of those smaller molecules. We have a total of 5 molecules in there overall. And then as you decrease the volume and push it down on the far right, we have now a higher proportion of those larger molecules. So there's only 4 total molecules occupying that smaller space. So by undergoing the reaction, the system went from having 5 total gas molecules to only 4 total gas molecules, and thus relieved a little bit of the pressure as the volume was decreased. Okay, maybe this figure wasn't worth the effort, but there it is. Okay, now there's one last thing that we can talk about. Not just changes by adding and removing products or reactants, or by changing the volume, but what about temperature? So up until now, all of these systems have shifted to restore equilibrium by making everything equal to the equilibrium constant K. And before and after the change, K was the same value because it's a constant. But it's a little bit different for temperature. K is actually a function of temperature. So as the temperature changes, the value of K changes. And in future classes, you can learn the math behind this and learn how you can figure out the temperature dependence of K and things. But for now, it's just enough to say that, well, the reason temperature changes will perturb a system away from equilibrium, even if all the concentrations remain constant, is because K itself is changing, and the concentrations must chase to follow it. So how K changes as a function of temperature, like I said, can be complicated, but whether it goes up or whether it goes down ends up being really simple. And it depends on whether the reaction is exothermic or endothermic. So here's the neat little trick. If a reaction is exothermic, then we will write heat as if it is a product. Now, heat isn't a product in the same way that the rest of these things are. We're not going to collect a certain number of grams of heat at the end. I can't talk about moles of heat, etc. But I think it makes sense for an exothermic reaction, or in other words, if delta H of reaction is less than 0, it's a negative number, then we can write heat as if it is a product. And now if I increase the temperature, then it is as if I've added a product. And so for this reaction, it's going to shift left. And if I decrease the temperature, it will be as if I've removed product, and so that will shift the reaction to the right. And this is for exothermic reactions, which the one up here is an example of an exothermic reaction. If you have an endothermic reaction, then you would add heat on the reactant side. And so if I increase the temperature for an endothermic reaction, then it is as if I've added now reactant, and that will shift to the right. And for an endothermic reaction, if I decrease T, then that will be as if I have removed reactant, and it will shift the reaction to the left. And again, what's really happening is that K is dropping in this case, and K is increasing in this case. K is increasing in this case, and K is decreasing in value in this case. But we can just talk about it as if we're adding product for exothermic reactions or reactant for endothermic reactions. Apply Le Chatelier's principle the same as we do for adding and removing other reactants and products. Okay, now equilibrium is not always the most important thing to consider in an industrial setting. For example, this reaction, I've said several times now in lectures, is a hugely important reaction in the chemical industry. And so people make ammonia by the thousands of gallons a day. And when they do so, they have to come to terms with the fact that it's an equilibrium reaction. They can't just mix nitrogen and hydrogen and expect it all to go to product. It's going to get stuck halfway through. And so you might think that if they want to drive this reaction to the right, because it's an exothermic reaction, that they should run it at low temperatures, like put their reaction chamber in a refrigerator. And the reality is these reactions in industry are carried out at high temperatures because equilibrium is only one factor, kinetics is the other factor. So if I run my reaction in a refrigerator, I will get more ammonia in the end, but it might take me 10 years. And the factory isn't willing to wait that long. If we run the reaction at a higher temperature, maybe we get less ammonia, but at least it finishes in a timely fashion, and time is money. And also what they really do is they will have some way of extracting the ammonia as the process proceeds. Namely, they could have like a cold surface somewhere in the reaction chamber where ammonia can condense, and ammonia will condense much more readily than either of these two. And once it condenses and turns into liquid, it's an easy matter to extract it from the reaction chamber. And that way, they actually are able to drive the reaction to the right by continually removing product. So anyway, just wanted to point that out. And then one last thing, what if I add a catalyst? We're talking about affecting this reaction, changing things, adding and removing things. And a natural question is to say, if I add a catalyst, is that going to speed up the forward reaction and give me more product? And the problem is that a catalyst provides a different pathway for the reaction to occur, and that pathway applies in both directions. So if I add a catalyst that makes this forward reaction go faster, it will always make the reverse reaction go faster in a commensurate way, such that the equilibrium position is not affected by the catalyst whatsoever. A catalyst will ensure that you reach equilibrium faster, but you'll reach the exact same final state in the end. Okay, and that's it for chapter 15.